So we'll consider this adaptive control. Okay, in your fifth unit, you have this topic, right? Adaptive control. And we have discussed the introduction of this in that first unit, CNC adaptive control, right? I told you that in adaptive control, basically what trying to do is you're trying to make sure that the system adapts to the situation, okay, that to the manufacturing situation, okay, either it be turning, milling, okay, it adapts to the situation prevailing, okay. When it is processing the part, it will adapt. Like if it finds that the vibration is more, okay, it will correct certain parameters so that the problem is solved. If at all productivity is to increase, right, the time, for example, instead of doing it in 5 minutes, if possible you can do it in 2 or 3 minutes, it is very productive, right? That counts as productivity. So even that is possible, we'll see how. So this, as it says, it is a logical extension of the CNC mechanism, right? CNC mechanism, you already have a your microcontroller that is deciding the tool motions, right, or the workpiece motion as is required. So a logical extension of that, you have this adaptive control that you see in CNC mechanism, cutting speed and feed rates are prescribed by the part programmer. The part programmer has to specify what is the speed, right, cutting speed, and what is the feed rate to be maintained. Now, how do you determine the cutting speed and feed? It depends on the knowledge and experience of the programmer, right? The one who is writing the program. Now, besides writing the geometrical data, right, where should the tool go to? But what is the speed of the workpiece and the feed rate to be maintained of the tool? That also has to be specified, right? That depends on what? The programmer's capability, his knowledge about the all these factors, right? Workpiece, what is the workpiece, what is the tool material, what is the coolant condition, and several other factors. So you see, in adaptive control, by contrast, in adaptive control machining, there is improvement in the production rate and reduction in the machining cost as a result of calculating and setting of optimal parameters during machining. So what we are trying to ensure is that only optimal parameters are being set so that there is improvement in the production rate. I told you that instead of doing in 3 minutes, maybe we can achieve it in 2.5 minutes or 2 minutes, right? And reduction in the machining cost also will reduce. Time is also another factor, right? Like if the time is less, then your cost will also be affected, it will also get down. Other thing is your machines would be safe, your part would be safe, right? All these are benefits. We'll see how we can achieve the adaptive control technology, okay, with these optimal parameters as we are talking about. You see, adaptive control machining originated in the early 1970s, sponsored by the US Air Force, okay. Initial adaptive control were based on analog devices representing that technology at that level. So you see, at that time they had hardwired devices, right? Presently we have softwares, isn't it? You feed the programs, you can change the strategy, right? The strategy with which the adaptive control system works, right? That it changes the process parameters is dependent on the software technology now, the programs, okay. So today adaptive control, as I was talking about, uses microprocessor based controls, and it's typically integrated with an existing CNC system. You have an integration, okay. The CNC system, the whole system is designed. When you are designing this CNC system, you'll integrate the adaptive control system also, okay. You see, what is this adaptive control machining, okay. Basically this adaptive control technology is applied to uh, uh, technology fields other than manufacturing, but we will see in the context of manufacturing, okay. That is adaptive control machining, that's why it says. So you see, for machining operation, the term adaptive control, AC, denotes control systems that measure certain output variables and uses to control speed or feed, right? So it will measure certain parameters, certain variables is what you call, okay? It will measure certain variables and will use that data to control the speed or feed, okay? Speed of the workpiece, speed of the tool, or feed rate, okay? So is the case. Some of the process variables that have been used in AC machining systems include spindle deflection, okay? force, torque, cutting temperature, horsepower. So you see, these are all being measured. How? With the help of sensors. I'll show you this diagram in the next page. That will be clear. You see, this is that diagram. Starts with your CNC system. Okay, you have a CNC system in place. Okay, it is giving out the drive commands based on the program. Okay, fed to the CNC machine. It is giving out the drive commands that the tool should move so and so in so and so contour in so and so fashion, right? And with maintaining so and so speeds and feeds, speed of the tool for speed of the workpiece, okay, and feed rate of the tool, right? It will give out the commands to the machine tool, and the machine tool perform the machining process. Now, when it is being performed, your sensors, okay, will measure some variables. What are those variables? I told you here. Some it could be spindle deflection, it could be spindle force, torque, cutting temperature even is one variable. Okay, is the temperature getting too high, right? Sensors will sense. Horsepower also. All these are being measured, okay, and given to the adaptive controller. The adaptive controller will take these measured variables, and based out of either constraints or a strategy or a performance index, it will send out the feed rate and speed corrections. Okay, so this is a general one. Okay, we are just discussing adaptive control system. We have two categories in adaptive control. There is adaptive control with optimization, adaptive control with constraints. Okay, this is a general one. We are just discussing what is adaptive control technology. Okay, so when it is with constraints considering, then you have adaptive control system with constraints. So that's why these three things are there. It could be a constraint, it could be a strategy, it could be a performance index. Okay, in on your optimization, you will consider this performance index itself. Okay, so based out of the strategy given to it, it will send out the feed rate and speed corrections. For example, the temperature was getting too high, so you will decrease the speed and feed rate. Okay, so that the temperature can be, and as soon as the sensors sense that because of the decrease of feed rate the temperature is getting normal, those measures will, that feed rate will continue. Okay, so as and when the part geometry is changing, as and when the tool position is changing, you have different situations, right? So this is what the adaptive control technology is: adapt to the situation. Okay, so the backbone of it is either you are imposing constraints, either you are giving it a strategy or a performance index. Okay, so it is based on this that the controller will decide what to do. Okay, is it clear so far? Adaptive control technology. Yes. Okay, so you see, adaptive control is basically a feedback system, isn't it? That's the backbone of it. There has to be a feedback. A feedback is required so that that treats the CNC as an internal unit, and it means in which the machining variables automatically adapt themselves to the actual conditions of the machining process. Right? That's what is happening. Machining variables, you're trying to what do you call? Basically, adapt to the situation, right? To the actual conditions, what is happening ongoing in the machining process. IP is your performance index. Okay, we'll see what is this performance index. Is usually an economic function such as maximum production rate or minimum machining cost, right? You want to either, these are basically the objectives, you can say. You want to have a maximum production rate or minimum machining cost. Depends on what is that it is, what is it that you are trying to achieve. Okay. Now, way to use the adaptive control technology. Okay, it is not suitable for every machining situation. We'll see why. These are the following characteristics that you can use. Okay, different situations. In process time consumes a significant portion of the machining cycle time. When you're in process time, okay, if it is a if it consumes a major part of the machining cycle time. Okay, for example, the tool that machine operator, okay, required is has to be very skilled, for example. Okay, so you have to spend some time, the operator has to give more effort, right, in order to maintain that speed rate, feed, etc. So all of that will increase your in process time, right? So the time required for processing, if it is more, okay, as in case of a milling, for example, right, milling and turning. Okay, so if it consumes a significant portion, yes, you have to implement this, otherwise it is not useful, right? If it is only a small part of your machining cycle, then it is not beneficial to implement this technology. Other thing, significant sources of variability in the job. You see, there are a lot of variability sources. For example, there could be vibration, right? It could be because of a problem with the tool. The tool is not mounted properly, or the or the machine itself is too old, for example, and there are vibrations. So you don't know where from the vibrations will come. So the sources of variability, in the sense, you don't know what could vary, okay, or the sources of variability are more. Then your adaptive system will compensate for it, right? That's what it is there for. So in that case, it is very suitable. Other thing, cost of operating the machine tool is high. So as I told you, skilled workers are required, for example, and it becomes very difficult for him to monitor that tool movements, etc., for complex or complicated geometries. Then you have to implement this adaptive control technology. Other thing is, typical jobs involve the steel, titanium, and high strength alloys. So these are the typical jobs that are processed, okay, with the help of this adaptive control technology. Clear so far? Now you see functions. The three basic functions of an adaptive control are these: identification, decision, and modification. Isn't it? It's quite intuitive, right? That you have to firstly identify, right, and then make a decision, and then make some modification based out of that decision, isn't it? So main idea of AC is the improvement of the cutting process, right? That's what you are doing. You want to improve the cutting process by automatic online determination of speed and or cutting, right? So AC is basically a feedback system in which cutting speed and feed automatically adapt themselves to the actual condition of the process and are varied accordingly to the changes in the work conditions as the work progresses, as we have discussed, right? So you see, as for the identification function, what are you going to identify? You will firstly determine the current performance of the process or system, isn't it? You'll see how is it performing now, right? That's the first step you have to identify, so that you can know whether it is performing to the maximum possible level it can perform, or is it not. That's why identification function is concerned with determining the current value of this performance measure by making use of the feedback data from the process. So that feedback data, which is coming from the sensors, will be taken to calculate this performance, right? Decision: once the system performance is determined, the next function is to decide how the control mechanism should be adjusted to improve the process performance, right? You have to decide how should we what should be done, basically, right? Decision. So the decision procedure is carried out by means of a pre-programmed logic provided by the designer. So this designer will give that logic. This is what is most important, you can say. It is based on this logic that the decision is taken, right? Like for example, you want to have maximum production rate. That is one what do you call aspect to look at. So the logic could be based out of that particular strategy, or it could be because of machining cost, right? Or it could be because of that you want to have the quality, precision and accuracy is much required. So based out of these pre-programmed logics provided by the designer, the decision procedure is carried out, okay. Now once that is done, you're going to modify it, right? Third AC function is to implement the decision. Whatever decision has been taken, you are going to implement it. Basically this is the, you see, logic function modification is concerned. As a decision function is a logic function, right? Now here you are having a physical or mechanical change in the system, isn't it? Modification, basically the tool movement, etc. That the speed rate to be changed. So there is a physical process happening, isn't it? So modification is concerned with a physical or mechanical change in the system. Modification involves changing the system parameters or variables so as to drive the process towards a more optimal state, isn't it? We're trying to change those process parameters so that we proceed towards a more optimal state, right? Is it clear so far? The functions of an adaptive control system, right? Basic functions. No doubts?
Sir, actually this function where it is used, sir, actually.
No, you see, what we are trying to say is the adaptive control has three functions. Okay, the three functions are, it has to firstly identify the performance, current performance, right? Because that's what you do, right? For example, you go to a company, right? You are asked to increase the performance level, right? Maybe it could be the sales, right? So you'll firstly identify what is the current performance, right? You'll make a decision, right, based on your logic, like what is to be done. You'll decide, and then you will implement it. That's a modification. You understand what this adaptive control technology is? When it comes to machining, we are trying to firstly identify the performance, like what maybe the cutting conditions. You will see how is the temperature, what is the temperature, okay, what is the quality being produced right now. You'll see all these things. Second thing, you will make a decision what is to be changed. If the temperature is too high, maybe I should decrease the feed rate. Okay, that is the decision that you are trying to uh, implement. Okay, so decisions will be finalized, what is to be done. Implementation, you will make it using the tool, right? The adaptive control will send out instructions to the tool to either change the feed rate or cutting speed, or coolant maybe required is more. Okay, because of the temperature being high, maybe the coolant required is more. So all these are modification, basically physical processes which are to be done, right? Is it clear, 389?
Yes, sir.
Okay, so you see now the classification, we have basically two classification. The third one that you're seeing, geometric adaptive control, that is applied to grinding or finishing operations. Okay, but in our syllabus we are looking for only machining kind of operations. So when it comes to the context of machining operations, we have two classifications of adaptive control systems. What are those? Adaptive control with optimization, adaptive control with constraints. Okay, these are the two things. ACO. O stands for optimization, C stands for constraints, like that. Okay, so this is that abbreviation will follow, okay, from now on. So you see, when it comes to adaptive control with constraints, in these are the systems in which machining conditions such as spindle speed, feed rate are maximized within the prescribed limits of machines, and tool constraints such as maximum torque, force, or horsepower. You see, when we come to the machine, every machine has got some constraints, right? The maximum torque it can produce, the maximum force it can give out to the machine tool, the maximum horsepower it has, right? These are machine or tool constraints. Like for example, the tool can only handle so and so temperature, maybe 1200 degrees centigrade. Okay, that is a constraint for the tool. That it can only handle certain deflection, maybe 4 5 mm it can handle, after that it will break. So these limits you'll consider, and you'll try to maximize what, the feed rate and the spindle speed. Okay, because if these increase, if the feed rate and spindle speed increase, you'll have higher production rate, isn't it? The tool being moving fastly will lead to what, reduced production time, right? So that is what you're trying to maximize, feed rate and spindle speed, considering in mind the limits that you have of the machine and the tool. Is it clear? That's the gist of adaptive control with constraints. Okay, so you see, in AC system, the correct feed and speed are automatically found, and it is not necessary to spend efforts on calculations of optimum speeds and speeds. Okay, so this system is what is ensuring, right, that we do not have to do calculations, right? Lengthy, complicated calculation. The system will do it. Okay, based out of these constraints. Okay, based out of the data that we are giving it, it will calculate at what point of processing should I maintain this feed rate, should I maintain this speed. Okay, so automatically found, and it is not necessary to do that calculations. It is left to the adaptive control controller. Okay, the controller is what will implement, isn't it? The controller will give out the instructions. So AC systems do not utilize the performance index and are based on maximizing. So you see, this performance index is basically for your adaptive control with optimization. That is why this point is there, that we are basically trying to have a contrast here. Okay, that ECC constraint systems, they do not utilize the performance index, but what they do, they're based on maximizing a machining variable. As I told you, it could be either feed rate, subject to process and machine constraints, allowable cutting force, as I was talking about. These are all constraints, right? Cutting force on the tool, maximum power of the machine. So within these limits, we're trying to maximize the machining variables. Okay. Objective of most CCC type systems is to increase the MRR. MRR is what? Metal removal rate, right? You might have heard this term in the manufacturing subject. Metal removal rate, the rate at which material is being removed. Okay. So more the chips coming out, more is the material removal rate, right? That's what. So objective of most adaptive control with constraint systems is to increase the material removal rate. Okay, metal removal rate during rough cutting operations. Okay, is it clear so far? Okay, you see, now we'll see an example. To maximize the machining feed rate while maintaining a constant load on the cutter. For example, this is what we are trying to do, that I want to have a maximum feed rate while considering the fact that there should be a constant load on the cutter. The cutter should not be having varying loads. Okay, it should only have a constant load. For example, maybe 1000 newtons. Okay, so based on this 1000 newtons, you will see at different points of time, you will see whether the load maintained is 1000 or not. If it is not 1000, you will make it 1000. How? You'll change the depth of cut, for example. Okay, when there are you see, maintaining a constant load on the cutter despite variations in width and depth of cut. So at different points of time, you will have different width and depth of cut, right? Depends on the part geometry. So what will happen is the load will change on the cutter, right? Based on geometry, because it is not contacting the same geometry all the time, right? The contact surface is not same. So the width and depth of cut will change, and therefore the cutter load will change. So we are trying to ensure that a constant load is maintained. Okay, why? Because we want to maximize the feed rate. Okay, so in a normal CNC system, the feed rate is programmed to accommodate the largest width and depth of in a particular cut, and this small feed rate is maintained along the entire cut, right? As a result, the machining rate is reduced. You see, problem with the normal CNC system is the feed rate is already given. This feed rate is to be performed. Okay, even though you see, they are set based on the largest width and depth of cut, isn't it? Because the largest width and depth of cut will have a more load on the tool, right? I will show you the example. You see here, able to see the example, right? You see, you have a cutter, right? This tool. First case, you are having variable depth of cut. You see, the depth of cut is increasing as we go from left to right. The depth of cut is increasing. You see here, increased. Here, the width is increasing, right? As we move from left to right, the width here was less, the width there is more. You see? Now you see the problem is, in conventional, what you're doing, the feed rate is maintained constant. Based on what? Based on the maximum depth of cut. Because you see, the more depth of cut you give, the higher is the load on the cutter. Do we agree? Right? So here it will have the maximum load, isn't it? So the feed rate has to be decided based on this. In conventional systems, you will decide the feed rate based on this. The rest of the time, you can have a maximum, you can have more feed rate, right? Because the depth of cut is not much. But conventionally, you will maintain the same feed rate all throughout. So you cannot utilize this opportunity, right? Adaptive system utilizes that opportunity, that it will increase the feed rate as it senses that the depth of cut is reducing, right? Similar for width, right? As you see, the width here is more, the cutter load would be more here. So based on this cutter load, you will decide the feed rate, which is this. So this conventionally on CNC, you will use the same feed rate throughout as we go from left to right. But adaptive, what it does, when it moves from lower depth widths to higher widths, okay, what it will do, it will decrease the feed rate. Why? Because we want to have a constant load, constant cutter load, right? Is it understood what I'm trying to demonstrate? Yes. Okay, so that's what we are trying to ensure. This adaptive control technology utilizes this opportunity that we can increase the feed rate at particular points of the workpiece, right? So that we can have that constant cutter load. Okay, if this feed rate is more, as I told you, the production rate would be more, right? We can process the part faster. So the adaptive system utilizes this opportunity. Conventional system does not. It is only based on the maximum what do you call cutter load, right? So all other points, it will maintain that same feed rate, although it could have been increased. Adaptive control implements that. Okay, I hope the concept is clear. So that's what this whole thing is about. Okay, a normal CNC system feed rate is programmed to accommodate the largest width and depth, as I was mentioning, and that small feed rate is maintained along the entire cut, and because of this the machine rate is reduced. By contrast, our ACC system, adaptive control with constraint system, maximum allowable load on the cutter is programmed, right? We are trying to ensure that this maximum allowable load is continued. Okay, for example, the cutting force. Okay, as a result, when the width or depth of cutter is small, feed rate is high, right? We saw when either the width or depth of cutter increase, the feed rate is automatically reduced, and consequently the allowable load on the cutter is not exceeded. As soon as the cutter load is increasing because of the variable width and depth of cut, it will change the feed rate. That's what is happening. Okay, as simple. The result is average feed with ACC is much larger than its programmed counterpart, right? In your conventional programming, CNC programming, you will only ensure that smaller feed rate. But here you are having this average feed rate, right? It is changing. So the average, if you compare of the two, this is much larger. Adaptive one is more larger, right? Okay, you see, this is the basic structure of ACC system for turning. If you apply to turning, for example, okay, this is what will happen. So you have lathe, you have force sensors, position and velocity sensors, right? The sensors will give out the data. Okay, what will happen is basically, you see, I'll discuss the components first. There is an adaptive control routine. Basically, in the programs have routines, right? Sub programs, you can call it. Adaptive control routine, feedback routine is also there. Okay, agreed. So what is happening is, based on the force sensor, that force value is taken, cutter force. It will be amplified. These are all electronics, okay? Amplified so that it can be given to the control unit, this control routine. So what the computer will do is it will see, it will compare the force which is actually there present, actual working conditions, okay? That is the actual working cutting force, right? It will take that and it will measure it with the reference force, okay? And it will check whether there is change in it. Like for example, our reference force was 1000 newtons. The force that is actually observed, okay, in the current cutting condition is maybe 800 newton. What is the difference? 200. So if this is 800 and we have a reference of 1000, that means we can have a cutting force up to 1000, right? Allowable force is up to 1000. Beyond that, it will fail. So but it currently it is 800. So we will try to ensure that that 200 difference is being minimized now. The adaptive control unit will ensure that, okay? Spindle speed feed limits will be given to it, right? And then that feed rate routine will change the feed rate. How should I change the feed rate so that this 200 newton I can utilize this, right? 800, if I can make it to 1000, then it'll have a higher production rate, right? So that feed rate routine will decide. It will implement that longitudinal axis, basically whatever axis is to be given that control, it will give. Okay, this is when applied to turning. Okay, so if that error, when we are continuously checking that difference, okay, cutting force, what is being actual in the actual working conditions, and the reference value we have. So difference of that is the error. So if the error is less, right, we are continuously checking. As soon as we see that the error is zero, no changes are being made to the feed rate. If it found that there is a change, then it will change, right? Positive difference, it will increase the feed rate. Negative difference, it will decrease the feed rate. Very simple, right? Clear? You see, 1500 was the initial force. Okay. But then, oh, I'm sorry, 1500 is what we want to maintain. Okay. I told you, right? There is something, a constant load that we can maintain. So this is what we are trying to maintain, the cutter load. I want it to be 1500. How do I ensure? Initially, the feed rate was more. As soon as it was found that there is what do you call lesser load, okay, on the machine tool, then it will do what? It will decrease. I'm sorry, there is more load actually, right? Only when there is more load you will decrease the feed rate, right? Because if you move with more feed rate, there is more load on the cutter, right? Common sense. So if it finds that the load is more, it will decrease the feed rate, right? You see here what we're trying to do, we're trying to vary the depth of cut. A is the depth of cut. Okay. Initially it was 2 mm, right? From 0, it went on to 2. You see, from 0, it went on to 2. So as soon as we are moving on to 2, initially it was less, right? So we maintain 0.5. But now, as soon as we are now moving on to 2 mm of depth of cut, will decrease the feed rate, because as I told you, more depth of cut, more load on the cutter, right? So that feed rate will be maintained until when? Until you have a more depth of cut. So from 2 mm depth of cut, you are moving on to 4 mm depth of cut. So when there is increase here, there is decrease in the feed rate. So the adaptive control strategy is what is ensuring that the feed rate is changed as we have a change in the depth of cut, so that we have a constant load on the cutter. That's what this graph, these all graphs mean. Is it clear or doubts?